Let's look at some examples of some more unusual stationary point questions. So previously I've given you an original function, asked you to find the stationary points, and subbing the x values to find the y coordinate. For this one, we're given some generic forms of equations and given some information about points and a stationary point, and then having to find the original coefficients or the original equation. So it's almost working backwards. So let's look at example 1. We've got y equals ax squared plus bx plus c, passes through point 0, negative 1, and has a stationary point at 2, negative 9. Find a, b, and c. So there's a few ways you can do this. I like to look at that first point there, 0, negative 1. You can tell that is our intercept. So if I sub in 0 for x, I'm going to get y equals c, so therefore c must be negative 1. So because it passed through that point, now remember they're x and y, so you just sub them in. So I'll do the whole process, but you might get there straight away. We'd get a times 0 squared plus b times 0 plus c, so therefore c equals negative 1. So we've got one of the answers already. We know it has a stationary point at 2, negative 9, and we know stationary points occur when the derivative is equal to 0. So let's find the derivative. So dy dx would be, in terms, now a, b, and c, we're thinking they're just constants. So just treat them like whole numbers. So times the power of 2 down the front, you get 2ax plus b, and c would drop off. Doesn't matter because we knew it was negative 1 anyway. So we're solving when that equals to 0. We know it's going to be a stationary point, and we know it's got a stationary point at x equals 2. So therefore, we can sub in dy dx when x is 2, it's just going to be 4a plus b equals to 0. And that's one equation. We also know that the point 2, negative 9 is a point on the original function. So we can find a second equation by subbing in 2 and negative 9. So negative 9 is our y values. And we've got 2, so that'd be 4a plus 2b minus 1. And then let's rearrange that, plus the 1 over, gives you negative 8. 4a plus 2b equals negative 8. We can even divide everything by 2 if you wanted to. Negative 4 equals 2a plus b. So now we've got two equations. So there's our two equations. We have enough information to find a and b. So I'm going to call this one equation 1, and this can be equation 2. To get them to drop off, I've got b's in both, so let's just minus one equation from the other. Let's go equation 1 minus equation 2. So I'd get 4a plus b equals 0, and 2a plus b equals negative 4. And if I'm minusing all that, I would get 4a minus 2a is 2a, b minus b is 0. Then we get 0 minus negative 4 gives us positive 4, so therefore a is 2. And then we can substitute that into either equation to find b. So 4a plus b equals 0. So we end up getting 4 times 2 plus b equals 0 from equation 1. And therefore b would be negative 8. So final equation, we've got a, b, and where's c gone? All the way up there. So we'd get 2x squared minus 8x minus 1 gives us that equation. So there's a little bit going on in there. There's some simultaneous equations, but once you've got the stationary point, you can sub in the stuff that you know to try and find those coefficients. Let's have a look at another one. A little bit trickier. This one, we've got a curve y equals ax squared plus bx plus 12 and a stationary point at 113. So find a and b. So we know the point 113 goes into there. So y is 13, x is 1. So therefore we'd have 1 squared is 1 times a, b times 1 plus 12. So we end up getting, therefore, and I'm going to put the 1a plus 1b plus 12 equals 13. So we can take that over the other side. 1a plus b equals 1. So there's minus 12 from both sides. So that's one of the points. The other point we can find is because we know the stationary point, which is the derivative. So let's go dy dx. I might change color. So dy dx, so at x equals 1, we know dy dx equals 0. So dy dx, we just do the derivative. We'd have 2ax plus b equals 0. So therefore, at 1, we get 2a plus b equals 0. X equals 1. So therefore, 2a plus b equals 0. Again, two equations. Call them equation 1, equation 2. We want them to drop off. So let's go 2 minus 1 here, just so I get a positive a. So 2a plus b equals 0 and a plus b equals 1. And I'm subtracting. So I end up getting a equals negative 1, and then sub that back in to find b. So negative 1 plus b equals 1, so b must be 2. Okay, so just to recap, if you know the stationary point, we find the derivative, set it to equal 0, and we can take the x value of that stationary point and sub it in to find our equations. Now, once we've got a couple of equations with two unknowns, we can use simultaneous equations to find a and b. So for both the first and the second examples, we had two equations with a and b in it. We had to find them using simultaneous equations. If you've got a y-intercept value, so you're subbing in x equals 0, you notice all those terms with a's and b's and any of those with an x and a coefficient at the front will drop off. So the final term there, or your c value, is going to be your intercept. So that's a shortcut rather than subbing in a point. So if you're not given that point up there as an intercept, like we were given it here as well, you'd have to sub in another point, so as an extra step. But just sub in what you know. Stationary points make the derivative equal to 0, and you should have enough information to cancel down and find those missing coefficients. Alright, all the best.